In this video, we're going to look at a phenomenon called Pascal's principle and the applications of it. So I've written down Pascal's principle here, which says, in an enclosed fluid, a change in pressure is transmitted to all parts of the fluid undiminished. A couple things to point out here. Enclosed is the right way to think about this. In an enclosed fluid, that means I have some sort of reservoir full of fluid, which is not open to the atmosphere. And a change in pressure, what this means, if I change the pressure in one particular portion, I change the pressure everywhere. A change in pressure is transmitted undiminished to all parts of the fluid. To see what we mean, it's useful to imagine a reservoir of fluid with two pistons attached. A piston is basically some sort of apparatus which is sealed so that no fluid can move around the sides of the piston, and I can move the piston up and down or side to side, however I have it oriented. So to show you what I mean, let me construct such an apparatus. So this entire thing is filled with a fluid, and I have constructed two pistons, which are here. So they're going to be attached to some sort of piston arm which can move these things up and down. So both this piston can move down or up, this one can move down or up. Okay, so this whole thing is filled with a fluid. It's at a particular pressure. First thing I want to notice is that these pistons are different sizes. In point of fact, this one has an area of the surface that's in contact with the fluid of A1. And this one has an area A2. The numbers are assigned arbitrarily, or it works both ways, but as I'm doing it, I think it's obvious that A1 is less than A2. This is just a bigger surface. Okay, fair enough. Now, let me ask you this. What if I take A1 and I push down on it, right? I actually lower A1 to here. I have traversed some distance, delta x. Now, what happens when I do that? I'm assuming that this fluid is incompressible. What happens when I do that is the pressure here, we'll call this P1, the pressure exerted on this piston increases. As I push it down, the pressure pushes back on me. Okay, well, there's also a pressure here, P2. What Pascal's principle says is that P1 has got to equal P2, right? A change in pressure in any part of the fluid is transmitted undiminished to all parts of the fluid. So we can get rid of the subscripts now just by saying that is some P. But that looks, actually, if I unpack what pressure is, that looks different for both of these surfaces. If this is true, the pressure on surface 1 can be characterized by F1, A1. A1 being the area of this surface, F1 being the force exerted, the total force exerted on that surface, and that is how I calculate the pressure, right? F1 divided by A1. Okay, well, what Pascal's principle says is that has to equal the pressure here, which I can write as F2, A2. That's very interesting because I have a ratio which has to be equal to another ratio. And if I compare terms across the ratios, I've already said that the denominator in this one is just bigger than the denominator over here. But if I am to preserve these ratios, what that means, this means that F2 has to be bigger than F1. That's very interesting. In effect, I have used Pascal's principle to make a force multiplier. See what happens? I apply a little bit of force here, and a lot of force is applied over here. The applications are endless, right? One really interesting place where you see this is when you get your oil changed in your car. Now, some places just have you drive over a pit, right? And there's a guy down in the pit. But some places put your car on a lift and they lift it up. How do they lift a car? That's really heavy. Well, they do it like this. There, you can probably see lifting up your car as some big cylinder. There's just a cylinder that's lifting it up. What that means is somewhere else, there is a small cylinder that's being compressed. It's being compressed by a small force is being applied, but a large force is being applied to your car. You see this with sometimes at tire change places they use to jack up cars. They have long jacks with a handle sticking off, and a guy will come over and pump the handle 10 or 12 times, and your car goes up. Right? What he's doing is he's compressing a small cylinder, which is then exerting a large force on a large cylinder to move your car up. You see this, you don't see it, but you use it every day you drive in your brake system. When you depress your brake pedal, you are depressing a small cylinder, which is then connected to a larger cylinder, which pushes your brake pads against your rotors, right? The common denominator here is fluid. You need brake fluid for your brakes to work. That's what brake fluid does. In a hydraulic jack, hydraulic means with water. They have water in here. A pneumatic jack uses highly compressed air to do the same idea, to do the same job. But in all these cases, you have two different cylinders. Now, it certainly seems that you're getting a free lunch here, right? But the saying in physics is there are no free lunches in physics. This is certainly nice to multiply the force, but we can't just get something for nothing here. There has to be a trade-off. And here's the trade-off. I've applied a force to this, right? I've applied F1. We'll assume I move down at a constant speed, which puts me in equilibrium, which means that the force I apply is the same as the force being applied back on the piston. They're balanced, right? So the force I apply is F1, and I move that piston down some delta X. We'll say delta X1. I'll subscript that. Well, what is this? Force times the displacement is work. Okay, well, this one moves up too. So conservation of energy is a thing. The amount of work I put in cannot be more than the amount of work I get out. That doesn't make sense. So what I have to say is not only are the pressures equal, the work I do has to equal the work that comes out of the system. So I have to say that this is equal to F2 delta X2, where delta X2 is going to be the distance that this piston moves up. Right? So you see what's happening. I've already said that F2 is greater than F1, which means this term is bigger than this term. But now I don't have a ratio, I have a multiplicative constant. So if F2 is bigger than F1, that means delta X2 has got to be smaller than delta X1. There's the trade-off. That's why when you press your brakes on your car, you move your foot 7 or 8 inches. Your brake pad moves about that far. It's really close to your rotor as it is. So when you depress your foot about this far, your brake pad moves just a little bit. So you get a lot of force, but you have to do the same amount or less work if you have some losses. And of course, we're always going to have losses. But we can't do more work. That's the point. That's why when that guy at the tire change place is jacking up your car, he has to crank that lever 10 or 12 times, and your car goes up, maybe 4 or 5 inches, enough for him to get the tire off. At the oil change place, if your car moves up a certain distance, there has to be a piston, a much longer piston somewhere that is compressing a long way to get your car to move up that far. So Pascal's principle leads to this idea of a force multiplier, which can be incredibly useful for we humans, but the trade-off is we have to do the same amount or less work. So any displacement that we're insisting the second piston undergo has to be smaller than the first one. Of course, it goes the other way, right? I can push down on this one, and this one goes up a whole long way. Of course, the force exerted here is less than the force I'm exerting over here. But you can probably think of some applications where that's not terrible. So that's Pascal's principle and in a nutshell, and one of the more popular applications of it.